Hi, guys. Let me get everybody in the classroom here, and then we'll start talking about stuff.
Good morning.
How are you?
Doing pretty well.
Good, good. Focus. Okay. All right. All right, let's just give it a second before I launch into things. Just some things to keep in mind. We're coming up on our last bit of stuff about for the class. It's very exciting. Hang on. So what we're going to do today, sorry, I just want to wait till everybody get here. All right. So what I'm going to do today is I'm going to cover our last bit of lecture material, which is chapter 9.4 and 9.5. Okay. The lecture example should be up online. I think I put them up over the weekend, so make sure you have them. If not, like I'll fill them out and then I'll scan them in, and then you guys can see the solution set for them today. So that'll be basically our last bit of lecture material, okay, which we'll be able to cover today, right? And then let's see, so then tomorrow, Wednesday and Thursday, essentially for class, like I won't have any new material that I'm going to be presenting, but what I'm going to do is I'll open up the class period to answer questions to get you guys prepped for the final exam, which is next week. So let's talk about the final exam, because I'm glad you guys have been very patient all the semester. We normally have this thing ironed out at the beginning of the semester. We, figured out very early like what percentage things are going to be, what the material is going to be, and all that. Semester is obviously very unusual circumstance-wise, and all sorts of things that are happening. So I appreciate your patience while we behind the scenes tried to figure out what was the best and most humane way to do a final exam for you. So I have some proposals for you, which I'll throw out to you. This is like what other instructors are doing, what we've kind of decided offline with the course coordinator and the other instructors. So normally the class has a final exam, which is cumulative for the whole semester, which means you would go back to the very beginning. You'd put things on like for probability, you'd have to do all those like those trees, to try to figure out what the probabilities were and all that, are continuous and discrete random variables. But what we've decided, because the semester's kind of stressful, right, as it is, we're going to try to lighten the load a little bit for the final exam and make it actually more like a midterm exam. So in terms of length, like the number of questions will be more like a midterm exam, and it will not be cumulative for the whole semester. We were thinking, and what we'd like to do is to make it so that it only covers the statistics portion, so the second half of the class. So that would basically be chapters 5, 6, and 7, and 9. So they're all the statistics functions that we've been doing, which is I've got a population that does this, I've got the variance, what's the let's calculate, a hypothesis test on it, let's figure out what the probabilities are, kind of like the test that you just took and the quizzes that we've been taking, in the last couple of weeks or so. So that the final exam is really more like a midterm exam, and it would just cover chapter 5, 6, 7, and 9, okay? So basically we're looking at normal distribution, binomials. We would have, we'd have both like data where we have population data where we also have proportions that we'd be dealing with too. So that's one thing. The other thing is because we came up with the weights at the beginning of the semester thinking the final would be cumulative. Normally the math department has our final exams be worth like 40%, which we decreased to 30. And then now, because it's only going to be like the second half of the class, just chapters 5 and above, then we thought that what we would do is, instead of having it be like a final exam where that exam is going to be worth 30%, of your overall grade, what we would do is we would take that exam and then we would lump it in with all the other midterms, so that you'd have the 3 midterms, excuse me, that you just took plus the finals. That would make it 4. And all those would be worth 70%. So each individually would be worth about, I think I calculated about 17, 18% percentage points for all of those exams. And so that's that's a possibility, right? To basically lump it in and just make it worth, all of the exams in the class are basically worth like 70%. So total, right? So we have the 3 midterms, and then we have our sort of pseudo final. Okay, so it's not like your whole thing, your whole grade for the semester is riding on this one test. It's basically equivalent to taking another midterm, and we're just going to lump it all into the same midterm pile. Okay, so that's one option. That's like basically what other sections are doing, to throw that in there. Also, we were scheduled to have a quiz on Thursday. And what I'd like to do is actually, I think you guys, you've had a lot of like assessments, right? And plus we have an exam coming up on Monday. So what I'd like to do is, we have a homework that's due on Thursday. That's basically 9.4, 9.3, 9.4, 9.5. Okay, those things got put up over the weekend. So I'd like to keep the homework due on Thursday because I think that will help you consolidate the material that you'll be tested on Monday. But then we won't have a quiz on Thursday, okay? But what I can do is, so we will have had 3 quizzes and I can drop the lowest quiz out of those 3, okay? So I said we were gonna have 4 quizzes and I dropped the lowest one, but now we'll have 3 quizzes and I'll drop the lowest one, okay? So then that way you guys, you don't have to worry about taking a quiz this Thursday since you just took a test on Monday and then you'll have to take another test. So I hope that sounds okay. I think I'm trying to make the workload reduced for you and the quantity of material reduced. You know, there's still things that I still need to test, you know, for a final exam type. Also, the final exam is not like, how do I say it? The whole group of us didn't come up with a general final that we've all agreed on. Each of us have our own final exams that we're doing and we're all grading our own stuff. So in the past, all the instructors got together and we did common grading. Like I would grade one question, somebody else would grade another question, that would be it. But now, like I'll be the one who's grading your exams coming up this Monday too. So that's so you'll have some consistency there as well. So that'll be good. I'm trying to think of what else. So I covered the quiz. Oh yeah, and then the final exam in terms of time. How long will you have to take it? We're looking at, because we're reducing the number of questions and making it more like a midterm, the course coordinator suggested making it be the length of a class, so 100 minutes, and then plus 20 minutes to upload. So I can set the timer to be 120 minutes, which is the length of the final exam, what it would have been normally, but that also includes the taking of the pictures and the scanning and the upload time. If you guys have any questions about that, then you can contact me offline. Also, I think what we'll do is we'll set up the same kind of window that we've done before, where I'll make it available on Monday afternoon. I know some of the other instructors are, excuse me, some of the other instructors are making it a very short availability window, or that you have to take it at a specific time. I prefer to kind of keep it like how we've been doing it this semester, which is I'll open up the exam at, say, 4 o'clock, and it'll be open for say 24 hours. So you'll have from Monday to Tuesday to take the exam. But remember, just like all the other exams, once you start it, the clock starts ticking. Okay, but I'll open up the window on Monday afternoon. Yeah, I think that's about it in terms of administrative stuff. I'm going to post an announcement just to kind of get it out there in writing, so that in case I've talked too fast, there's a lot of details that got missed. Don't sweat it, I'll post it out there. Okay, so the end result is no quiz on Thursday, homework due on Thursday. Okay, I think I can't remember if I set the mid-date at Thursday. I think I may end up postponing the due date on the homeworks, maybe by a couple of days, so that you guys have time, because we'll, you want to make sure that you have some time to do it. And then the next couple of days, you guys can come to class and ask me questions. We can kind of consider it a general review. I think your best bet for studying for the exam on Monday is to look at old homeworks. I think the homework questions are really good. And they kind of, generally test, how things, I mean, some of the questions are better than others, but they generally test you fairly well in terms of, like, how do you think about things. So if you want to come, you can ask me any questions on, homework stuff starting from chapter 5 and going forward. You don't have to just even focus on the homework that's due this week. Okay, so any questions? I kind of threw a lot of stuff out at you there. Anybody have any questions so far on what I just said? Put it into the chat if you want, or you can send me an email later if you want to do that. That's totally fine. But this is trying to keep it consistent with what the course coordinator has suggested, and also with what other instructors are doing. Okay, so this is trying to make that work, but also trying to make it so that it's an exam. So we're kind of testing, the stuff that you've done, in the statistics part of the semester without overburdening you with so much stuff, because it's kind of an unusual semester. Okay. All right. So with that said, let's go ahead and get started on our last bit of material. So this is chapter 9.4, which is what I'm going to start with right now, and then when we're done with that, we'll cruise into chapter 9.5. Okay, so chapter 9.4. So 9.4 is using binomial data these are our proportions, right? 5 out of 10 people say that kind of thing. So what we're going to do is hypothesis testing with 2 samples. So we're going to test our null hypothesis is that our proportion for our random sample of X is equal to our proportion for our random sample of Y. So if you remember when we did this with means, right, our sort of a continuous set of data, our mean, this was mu sub X equals mu sub Y. So this is the same type of a deal, only now we're dealing with proportions. P stands for our proportion, okay? So let's kind of write down, I'm going to try to give you some background material, but the formulas that you'll need in order to solve the examples, to solve the homework problems, to kind of consolidate what the general information is. I'll put a box around it and a couple stars so that you can know that that's the important bit, because there's some things we want to be able to derive to give you some background information. So let's talk about what this is. So we're talking about discrete sets of data. Okay. We're going to look at, we're going to use our likelihood criteria to help us come up with, kind of derive what we're actually doing, just so that you can kind of see where these formulas are coming from, just so I'm not pulling them out of thin air and just giving them to you. But I'm not going to spend a lot of time deriving things, but just so you know kind of like where stuff is coming from. So we're going to take a look at derivation of a z-test. This is a z-test for 2 proportions. Okay, and then we're using a z-test because often, when you're using a z-test, the number of samples that you're gathering are going to be fairly large. So you're going to be bounced out of the t-test degrees of freedom table, and like your sample sizes are going to be fairly big, especially when you have 2 proportions that you're dealing with. Okay, so I've got n Bernoulli trials for X successes. Okay, so X is we'll call X like our random variable for a particular experimental thing that we're doing. Okay, and remember our Bernoulli trials, this comes from, we do a binomial experiment where we assign a 1 to a success and a 0 to a failure. Okay, and then we sum all of these 1s and 0s up, which is the same thing as just summing up all the 1s, all the successes, right? And looking at out of n, I have X successes, right? So these Bernoulli trials, this is also each is assumed to be independent. And remember, we're using the z-test because our law of large numbers says, especially that as we poll larger and larger and larger numbers of people, even though it's a discrete set and it's binomial, the data themselves form into a normal distribution. Okay, so that's for one set for our random variable X. I've got my other M Bernoulli trials for Y successes. And I'm going to assume the Y random variable is also independent. Each trial is considered independent. That's part of what it means to be a Bernoulli trial, is independent. So when I look at the proportion for X, I'm looking at the total number of successes over the total number of trials for my X random variable. And then the same thing for my Y. Okay, so now our hypothesis, right? Remember at the very beginning, we said our hypothesis, null hypothesis, was that the proportion for X is equal to the proportion for Y, okay? So that's like our basic null hypothesis that we're testing when we think about it. I've got experiment here and experiment there, and then I want to see, are those proportions the same or not? My null hypothesis is that they're the same, okay? So these are where those proportions are coming from. Okay, so what we're doing is we're going to test whether p sub X and p sub Y, which are, you can think of this as the population mean. These are, let's see if I can get this straight, which are the true probabilities for success. Okay, this is like our mu sub X and mu sub Y. So we're going to test whether p sub X and p sub Y for X and Y treatments, right, for X and Y Bernoulli trials are equal at the alpha level. Alpha is whatever we set it to be, right? Your minimum alpha you typically want to be thinking about is 0.05 in order to be taken seriously, right, when you're doing this stuff. So, but alpha level, we typically specify that. If it isn't specified, you can assume it's going to be alpha 0.05. You can set that for yourself. Okay, so now we've got, like we have done before, we've got our 3 different possibilities, right? So I've got my null hypothesis that the probabilities, I'm sorry, the proportions, proportion of x, proportion of y equals each other, versus my alternative. This is our two-tailed test, right? That they're not equal to each other. Or I can do, my second one is my null hypothesis that they're equal x versus x greater than p of y. This is a one-tailed test. The probability of x is greater than, proportion of x is greater than proportion of y. This is our right-tailed. Okay. And our third possibility, our null hypothesis. You know where this is going. Px is less than p of y. This is our left-tailed. We're going to set this up just like we have been doing. Remember, this is like based on a z-table, a z-distribution. So where you can draw your normal curve, you can set up your boundaries for where your alpha, the shaded regions are. Okay, to think about it. I just want to call your attention when we think about this, right, our null hypothesis. Okay, so if I say my null hypothesis, px equals py, another way to write this is I can say my null hypothesis, px minus py equals 0, right? So that the difference in the two proportions is equal to 0. This is going to come into play, especially in 9.5, when we talk about confidence intervals and how do we use confidence intervals to do hypothesis testing. Okay, so I can also write this, okay, that there's no difference, right? If their difference is equal to 0, that there's no difference in their proportions of these two random variables. So I can write it like this, or I can write it like that. We're going to be talking about these things. So keep this in mind here, that I can subtract them and make it be equal. Okay, and then obviously my alternative hypothesis, I'd set it up like that. Okay, or greater than or less than. Okay. All right, so everybody have that sort of background stuff before I flip the page. Okay. Okay, so let me, I'm going to give you just a little bit of a derivation before I actually give you some of the formulas. So let's talk about our likelihood functions. Okay, so we're going to use our likelihood functions to derive like our whole z distribution for this. Our likelihood functions. Remember, we need to have a likelihood function that's going to give us an estimator for what we think this population proportion is going to be. So first, I'm going to let my lowercase omega equal to. It's a function of my two proportions, right? P of x, P of y. Okay, and y less than 1. So all we're saying here is that P of x could be equal to P of y, and they're both between 0 and 1. These are proportions, right? We expect them to be between 0 and 1. So I'm also going to let capital omega equal to still P of x, P of y. And individually speaking, P of x is between 0 and 1, and then P of y is between 0 and 1. Okay, this is more background than you need. It's a calculus-based class. We're engineers. We kind of want to know where some of the things are coming from. But like I said, you know, bear with me here. If it's not making a whole lot of sense, I will put boxes around the formulas and stuff that you need. Okay, so our likelihood function comes from here. L is going to equal to P of x raised to the x power. How many successes do I have? That's my proportion. This is like our probabilities, right? This goes back to our binomial, 1 minus P of x and minus x, right? Times py to the y, 1 minus py m minus y, right? Because remember, x is the number of successes that we have, n is the total number of trials, okay? These are independent, okay? So I'm going to multiply their probabilities essentially together. Probability of success, probability of failure, probability of success, probability of failure, okay? So this gives us our likelihood function. Now, like we did with our likelihood functions, right? We take the natural log, okay? And then we're going to take the derivative, set it equal to 0 to get our maximum. We're not going to go through it all. We would take partial derivatives, one for p of x, one for p of y. Take the derivative, set equal to 0. Okay, so those are our steps. Remember we did that, I think like back in chapter 4, okay, to figure out our maximum likelihood for it. So D oh, P equals 0. Okay, and then we're going to solve for P. That's generally speaking, right? But for what we're trying to do, right, we would do the individual ones. Now, for the first thing, what we would get when we do this, I'm going to shorten it. So when I get my expected value, right, for my proportion is going to be a pooled estimate, X plus Y all over N plus M. Here I'm going to put a box around it, and I'm going to put a star. You'll need that. Okay, so what this is a maximum likelihood estimate, or P, are basically like our generalized overarching population proportion under our null hypothesis, right, that says that these two are equal to each other. This is a pooled success proportion. Okay. P sub E, that's our maximum likelihood estimate. Remember we did like theta sub E, that was our estimator, okay, for that parameter that we're talking about. So we did all this stuff. I didn't show you all the miniature steps on it, right, but we get this P sub E for our pooled proportion, okay. So now what we would do to get P of X and P of Y, okay, so I'm going to solve the partial differentials. Right, so this is my partial differential of our likelihood function with respect to P of X. Set that equal to 0. I'm going to get P X E equals X over N. This is important. I'm going to do the same thing. Set that equal to 0. P X, oops, sorry, Y, that's a Y. Y sub E equals Y over M. And that's important. Okay, these here, let's see. These here are unrestricted maximum likelihood estimators for P of X and P of Y. It makes sense, right? I mean, for my X, I'm going to say number of successes over the number of trials. For my P of Y, my number of successes over the number of trials for my X random variable or my Y random variable. Okay, so these are our maximum likelihood estimators, and we're going to use them in our formulas, right, when we're thinking about how do I calculate this test statistic for my proportion, okay? But how we get there, okay, is we've got this likelihood function that's based on our proportions for X and for Y, okay? And then we're taking the derivatives. We've got this pooled maximum likelihood, and we have individual estimates for P of X and P of Y, okay? So, let's see. You guys all have this before I flip the page? Everybody's very quiet. Let me just talk really quick about our central limit theorem. Right, remember our central limit theorem, which says like, as I get larger and larger numbers, these things move into like a normal shaped curve. Okay, so this is going to be approximately normally distributed, which is great because that means I can use all my normal tables and my normal data.
Is there a difference between central limit theorem and normal and the theorem of large?
The theory of large numbers, yeah, they go hand in hand. It's basically like so central limit theorem and the law of large numbers, they go hand in hand in the sense that like as I increase my sample size, right, as I increase the number of polling that I'm doing, my n, right, as it gets bigger and bigger, my data tend toward central limit, which is the mean, right, and the shape becomes normally distributed. So when we have smaller sample sizes, that's why we say we're going to assume the data is normal. Well, when the number of samples gets, you know, fairly large, and we've even set like large as being like 30, which is actually quite small, right? But certainly as I go from like 30 to 100, I'm in a T distribution. When I am above 100, I'm in a Z distribution. They're both normally shaped curves, okay? But the central limit theorem is basically saying as I get larger numbers, things, our data tend toward a central limit, a central number, which is our mean on that bell-shaped curve. Does that make sense?
Yeah, they.
right, so it's approximately normally distributed. So what we're going to do is, generally speaking, before I write down the specific formula, right, so generally speaking, we're looking at x over n minus y over m, because remember, we're looking at the difference in two proportions, right, minus my expected value of x over n minus y over m. Okay, our expected value. This expected value is like, I've got my samples, I've got my population, right? And I'm going to divide that by the variance, the square root of my variance. Okay, so generally speaking, this is normally distributed. Okay, so under the assumptions from our null hypothesis, right, this right here, our null hypothesis states that the proportion for x and the proportion for y are equal to each other, right? So that means that my expected value of these two proportions, their difference is going to be equal to 0. That's my null hypothesis. That exactly is what it is. And then my variance, okay, is x over n minus y over m. We need to find an unbiased estimator for that. This, when I plug things in, I'm going to get p1 minus p over n plus p1 minus p over m. Okay, and then this becomes n plus m, right, combining with the fractions, p1 minus p all over n times m. Oops, there's an m there. We're going to talk about what this p means in just a second. So hold on to your ideas. This is our estimator for our, basically our population proportion. Okay, so the null hypothesis, we talk about basically our mean and our variance, okay, under the null hypothesis, so that I can use them to come up with a specific formula for my hypothesis testing on two proportions. Okay, so first off, I'm going to we talked about this before, my PE, my expected value estimator, plus y, n plus m, and I'm going to say my test statistic z is x over n minus y over m minus px minus py. This right here, I'll write this in a different color. This is our null hypothesis. Right here. So our null hypothesis says that the difference between them is 0, which is why when we did this with mu x minus mu y, right, and under the null hypothesis, that portion, that subtraction became 0. But we're just putting it down there because it's part of the overall, we're comparing samples to population. So I've got PE minus PE over n plus PE 1 minus PE all over m square rooted. Okay, we put a box around that and a star. Okay, so I'm not just kind of like throwing it out at you. I'm telling you like kind of a little bit about where it comes from. But let's talk about what our null hypothesis is and what our criteria are for rejecting and accepting. Okay, right-tailed, left-tailed, two-tailed. Okay, so let's see, start over here. So if our null hypothesis px equals py versus our alternative hypothesis px is greater than py, okay, so we're talking about a right-tailed test, right? We're going to reject the null hypothesis if our z value, our test certificate, test statistic is greater than z of alpha. Okay, it's a single-tailed test, so I don't divide alpha by 2. And note that this is a positive because we're on that right-tailed, that positive portion of my normal curve. My null hypothesis, px equals py, versus my alternative hypothesis, px less than py. Okay, so now we're going to reject our null hypothesis if our z, our test statistic, is less than or equal to minus d alpha. Now we're on that lower edge of our left-tailed curve. This is like what we've been doing so far. Nothing new here, but just kind of spelling it out for our proportions. Okay, and now for our two-tailed, our null hypothesis, px equals py versus alternative x does not equal to py. Remember, now we have z alpha divided by 2, so we're going to reject our null hypothesis if our z, right, is greater than or equal to positive z alpha over 2, or if z is less than or equal to minus z alpha over 2. As if it falls into one of the tail regions. Okay, so our three different possibilities: right-tailed, left-tailed, and two-tailed. Okay, so the same type of idea that we've been doing so far. Now, we're going to modify this a little bit. Okay, this was our expected value for our proportion. Okay, sometimes, often, what we'll do is we'll substitute P of E with P of X. This becomes P of X, 1 minus P of X, P of Y, 1 minus P of Y. You essentially get the same result either way. Okay, but we'll talk about cases where we'd actually be using that. So, you guys will have that before I turn the page. All right. Okay, so
Wait, sorry, can you go back for 1 second?
you bet. How's that?
Yeah. Okay, thank you.
Okay, so for two proportions, okay, we're actually going to split it up. Proportions. A px hat is our estimator, okay, for our x random variable. Right, we say because we don't know what the population proportion for x is. I've just gone out and I found like a sample, right? I've got x successes all over n samples for that. Same thing for y. We have y, okay. These are here, these here are our population proportions. And we can basically know that px and py are unknown. The whole point of what we're trying to do is to come up with a reasonable estimate for what our population proportions are going to be, right? You can imagine I have some idea, some experiment that I want to conduct. Ideally, I'm going to go out and ask everybody in the world, 7.5 billion people, right? What do they think? Yes or no? Do they agree with this, right? That would be my population proportion for my experiment of X. I do the same thing for my experiment of Y. Okay, it's not reasonable to be able to do that, to go ask the whole population of the United States or the whole population of the world or whatever. So what I do is I go out and I get a sample, N samples, and I ask that question. I get M samples and I ask the other question. I'm going to compare them. So I'm going to use these as estimates for my population proportion. Remember, that's all about what we're doing. Okay. So we have the standard error of the difference. Oops, running out of space. Standard error of the difference, which is our sigma of px minus, oops, sorry, our hypothesis px minus py. Okay, so this is the standard area of the difference of the two proportions. That's going to equal to, like, the variance for px plus the variance for py square rooted. And how that looks in reality is this: px 1 minus px all over n plus py 1 minus py all over, oops, that's an m, square rooted. Okay, and that gives us our standard error of the difference. Okay, I've got my individual, okay, estimator for px and py. Okay, when we do our examples, we would plug in our x hat and py hat into here. Okay, all right. Let's see. So yeah, I think there's a couple more things. I think I'll skip those just for clarity. All right, so let me take out my lecture examples for chapter 9.4, and we'll start working through some examples so you can see how this all holds together.
Can you go back for 1 second? Sorry.
You bet.
Thank you.
All right. Okay, so chapter 9.4, lecture examples, example number 1. So you've got a nursing home study. Found that 12 out of 34, so we're starting to read our proportion, 12 out of 34 randomly selected small nursing homes. So this is one set, so this is like our X data. Had vaccination rates less than 80%. 80% is just a way of describing the data. It has nothing to do with the statistics that we're going to do. 17 out of 24 is another proportion. Large nursing homes, this is our other variable, had vaccination rates less than 80%. So we're keeping them with the same experimental question. The things that are changing are we have small nursing home versus large nursing home. Our alpha 0.05, okay, we want to test the claim that there's no difference in the proportions between small and large homes with vaccination rates less than 80%. Okay, all right, so that's our question. Let's start setting up our proportions and then thinking about how we want to do this. So we're going to set it up the same way that we have been doing with our hypothesis, the statistic criteria and all that. Hypothesis. So our null hypothesis, right, is that our two proportions are going to be equal to each other versus, let's see, a difference, that there is no difference in proportions. So no difference implies a two-tailed test because they're not saying it should be greater or less than in the other one. So my alternative hypothesis is that the proportions are not equal. I need to set up my critical value. My critical values because it's two-tailed. So my alpha equals 0.05, but this is a two-tailed, which means I have to look up alpha over 2, okay? Let's just draw a quick picture. Okay, so our two-tailed test, right, we're splitting things up into two different pieces. So my alpha over 2 is 0.025. So this is 0.025, this is 0.025, area under the curve, okay, 0.025. So I need to look up on my Z table, alpha over 2, right? According to 0.025, we find that this is equal to plus or minus 1.96. This is our criteria here, positive 1.96, negative 1.96 on our table, okay? So it gives us our critical values. It's going to help us determine if our test statistic is in the critical region or not. Okay, so let's talk about our test statistic. Okay, so our test statistic, I need to look at PX hat, right? It's an estimator for my population for small nursing homes. So this is going to be X over N, which is 12 out of 34, which I made to a decimal, 0.35. Do the same thing for Y over M, which was 17 out of 24, which came out to be 0.71. So I have PX and PY. Okay. Now I need to, I'm going to use my old estimate here. So I'm going to say this is going to be X plus Y all over N plus M. So I'm going to go 12 plus 17 all over 34 plus 24, which I got was equal to 0.5. Okay, just came out that way. All right, so now this is all like prefetching before I actually calculate my test statistic. So my test statistic Z, let's write down the formula. EX hat minus PY hat minus our null hypothesis, PX minus PY, all over E1 minus PE all over N, 1 minus PE all over M. Here, let's plug things in. So I'm going to get 0.35 minus 0.71, and I'll write it out as this is going to be a 0 because our null hypothesis states that there's no difference between the two. You don't have to write out minus 0. I'm just showing you. Okay, so I'm going to plug things in. So this is 0.5, 1 minus 0.5 all over 34. 0.5, 1 minus 0.5 all over 24. Square rooted.
So if there was a difference in P's, like if one of them said less than 80% and one of them said less than 70%, then there would be a difference?
No, so that would be two different experimental questions. That's like comparing apples and oranges, and that's actually a flaw. When you read studies, you'll want to be looking for flaws like that. So if they say, well, in large nursing homes, 80%, less than 80% of the population is like this. In small nursing homes, it's less than 70%. Well, those are two different experimental questions. So I need to be able to compare and say, I'm looking for the proportion of people who have like vaccination rates that are less than 80%. So you can think about the 80% thing as being like not the numbers of people who have vaccinations, but like, you know, I need a whole battery of vaccinations, say per year, or per time period, or whatever, right? And so if I've only done 80% of those vaccinations, okay, I'm not even talking about all the different types of vaccines, but let's just say 80% of those vaccinations, I'm looking for a quantity of people who've had less than 80% of those vaccinations. So you want to be careful, because if I compare less than 80% and less than 70%, then I'm not comparing fully. And so what I want to do, if I want to compare those two populations, I'll need to truncate out the data on the 80%. I'll have to say, let's compare less than 70% on both. Okay, so that means I have to throw out these portions of people who have between 70 and 80% vaccination rate. It's not the 70 or 80% doesn't pertain to the numbers of people who've been vaccinated. It's 70 or 80% of all the vaccinations that need to be had.
Okay.
Does that make sense? It's a funny question, because I've got 80% and then I've got this proportion. So what does it mean? It's a kind of a confusing question. You have to be able to parse out like what's being asked, but you have to be very careful, because if you want to compare these things, you have to make sure that all parameters are the same. The only difference is this group comes from a large nursing home, this group comes from a category of a small nursing home, right? And so that's how we're thinking about it. And like that's the whole thing with the experimentation is, you know, maybe you've got some population of people, these are people in nursing homes, right? And so some population of people, and then I want to be able to tease out, compare only, like change only one parameter at a time. Otherwise, if you're changing multiple parameters at a time, it's hard to tease out like what actual parameter is causing the difference in statistics. So you want to be able to control for everything except for this one parameter, or I'm going to control for everything except for that one parameter. And then those things I need, that's the hypothesis that I'm testing. So right now the hypothesis that we're testing is that between small and large nursing homes, that's our two random variables, small and large nursing homes, between those two random variables, right? The parameter that we're testing is, you know, that these groups of people have less than 80% of the vaccinations that they need. Okay. It's confusing, but it's sort of like an experimental paradigm. We only want to control one thing at a time. So you have to be able to compare all things being equal, except this group comes from large, this group comes from small. Okay, so my test statistic is minus 2.70. Okay, when I add everything up and multiply it out. All right, so when I compare it, right, I'm looking at my graph, I'm like right here, minus 2.7. So you can kind of get a feeling for what our decision is going to be, right? So our decision-making process, we're going to say our test statistic, right, which is minus 2.70, is less than the negative portion of our critical value, right, which was negative 1.96. Therefore, right, we can reject our null hypothesis, okay, because it's falling within the critical region. And let's just write in words like, what does that mean exactly? So there is enough evidence. You only have to give me these two lines. I'm writing out how do we interpret this data just so that you know. So there is enough, evidence to reject the claim that there is no difference between proportions in small versus large nursing homes, that both of them, that each of them has, that have vaccination rates less than or equal to 80%. Okay, so 80% is just a criteria marker. We have all of these nursing homes out there, small and large, right? They're two different categories. Of those, which ones have vaccination rates less than or equal to 80%? Okay, so now within that, what proportions of the people within the small versus the large satisfy the criteria that they have less than 80%? Okay, well, so in the small nursing home, we have 12 out of 34. In the large nursing home, we have 17 out of 24. It looks like these are actually two very different proportions. Based on our statistic, at the alpha 0.05 level. Okay. So that's how we're thinking about it. You guys need more time to write this before I turn the page? Okay. I'm going to go to example 2. So example 2 says, a study found that in a random sample of 50 burglaries, 16% of criminals were arrested. In a random sample of 50 car thefts, 12% of criminals were arrested. So in this case, these are going to give us our proportion values, right? At the alpha 0.1 level, it can be concluded that the percentage of people who were arrested for burglaries was greater than the percentage of people who were arrested for car thefts. Okay, so let's think about what we're trying to do here. All right, so now let's do our hypothesis. Our hypothesis, null hypothesis, is of course the proportions are equal to each other, okay? Versus burglaries was greater. So it's giving us a clue about what type of alternative hypothesis testing we need to do. So it's greater than. So I'm going to say P1 is greater than P2. This is my claim. Okay. And it told me to do greater than. So that's how I need to do a one-tailed test. Okay, so now I only have to find one critical value. Because it's a right, greater than is a right tail. Right, my alpha is equal to 0.1, okay, which is a pretty high alpha, but that's okay. Okay, so here's my normal distribution. Okay, this is my alpha equals 0.1. That's the area under the curve. I'm looking for the line here, that z, that's going to give me that. So let's think about this one. So it's a right-tailed. So what I need to do is remember our z-test. The whole curve is equal to 1 minus. Remember our z gives us areas less than or equal to that. So I have to subtract out whatever the probability is that's less than this here. So this is going to be 0.9 is that area. This is 0.1. That's how we get this. So this is the probability that this is equal to 0.9. So to find out the z associated with 0.9, I'm going to get z1 minus alpha equals z 0.9, which is equal to positive, it's right tail, positive 1.285. And this comes from our table. Okay, so this is 1 minus 0.1 gives me 0.9. I need to look at z 0.9 because our z table tells us probability is less than or equal to this number. So my critical value is positive 1.28 roughly. Okay. So now I need to calculate my test statistic. Okay, so now, so I'm going to say if p x sub hat equals x over n, which is 0.16, right? Then I need to know what x is. This is x over n. So then this is out of 50 burglaries, right? Then x is equal to 0.16 times 50, because our n was equal to 50, right? Equal to 8. We'll do the same thing. If y sub hat equals y over m equals, we say 0.12, and y equals 0.12 times 50, y equals 6. So I found my individual x and my individual y values, just to let you know, because my pooled version, x plus y, all over n plus m, right? 8 plus 6 all over 50 plus 50, it's going to give me 0.14. Okay, so it gives you my piece of B. All right, so now let's calculate our z value, test statistic. Px hat minus py hat minus, this is our null hypothesis, all over, I'm just writing down the formula, PE, 1 minus PE over n, plus PE, 1 minus PE all over m, square rooted. Okay, so let's plug things in. Okay, so I'm going to get 0.16 minus 0.12 minus 0. I'm not going to write it out anymore. 0.14 times 0.86 all over 50 plus, I could just multiply it by 2, but I'll write it out so you can see. Square rooted. Okay, so I'm going to add, subtract, multiply, and divide. I'm going to get my test statistic is equal to 0.58. All right, so let's compare. So if our critical value is 1.2 and our test statistic is 0.58, 0.58. So we're looking at making a decision. Okay, so our decision, our test statistic, 0.58 is less than our critical value, which is 1.285, which means we're not going to reject, fail to reject our null hypothesis, our decision. Okay, so I'll write down in words like what that means, just so that you can have a feeling. All right, so this means that there is not enough evidence to support the claim that the percentage of people arrested for burglaries, right? Burglaries is greater than those arrested for car thefts. Okay, at the alpha 0.1 level. Okay, right? And that's the end of chapter 9.4. Okay, I'll scan this in, the lecture examples for 9.4, and I'll put it up later today. Right, so now let's take a look. We're gonna move on to 9.5. 9.5 is fairly quick. And it's based on like a lot of stuff that we've been doing before. We're gonna talk about doing confidence intervals for 2 samples is 9.5. We're also gonna talk about how I can use confidence intervals to help me do hypothesis testing. We'll talk about what that exactly means. Okay, so 9.5. Okay, 9.5 is confidence intervals for 2 samples. And we're going to do both our mean and our proportions. Okay, so we're going to look at confidence intervals for that. So we've got different cases for where the population variance is known, where the population variance is not known. And let's take a look. We're going to decode each of these. So we're going to do a z-test for when the population variances are known. Okay, so let's write down what our z-test is. Let's see. I'm going to write it like this. I've got my x minus y. This is like x bar minus y bar. This is plus or minus z alpha over 2, right? Because it's, remember, our confidence intervals are inherently two-tailed, right? So z alpha over 2, sigma x squared all over n plus sigma y squared all over m, square rooted. Okay, so what this means, I put a box around that, and then I've also put a star. What this means in terms of our confidence interval is, let me write it all the way out. So this is like saying x bar minus y bar. So this is our difference, plus or minus the variances, okay? So that's going to be minus z alpha over 2 squared over n plus sigma y squared over, that's a y squared over m, square rooted, is less than our population, y, which is less than x bar minus y bar, right? We're always looking at the difference in our 2 means here, plus z alpha over 2, sigma x squared over n, sigma y squared over m, square rooted. I'm going to put a box around this one too. You can write them both. Okay, they both represent our confidence intervals, right? We would write this as parentheses number, comma number, because I would get a number here. That would be my lower end when I subtracted, and my upper end would be when I added. Okay, but basically what we're saying is that the population difference, population of x random variable, population of y random variable, we don't know what the population of x and population of y are, but we can be 95% confident, 99% confident, whatever our confidence interval is, that the population difference, the difference between the 2 population means, is between this value and this value right here. Okay. All right, so I've got my lecture note examples for 9.5, and I'm going to do an example using this right here. Okay. This example 1 says we have a study using 2 random samples of 35 people each, so this gives us our N and our M. Found that the average amount of leisure time was 39.6 hours a week for group X, and they gave us an age range just to let us know that age is our characteristic that we're separating out these 2 random samples based on. So younger people versus older people. For group Y, the average amount of leisure time was this. Given that the population standard deviation for group X, so look, population standard deviation, this is, right, my big sigma. For group X was 6.3, and the population standard deviation for group Y, so this is, right, so this tells us when you're told the population standard deviation or population variance, you can use a Z-test. Okay, we'll spell it out for you like that. Was that at the alpha 0.05 level, are these 2 groups statistically significantly different? Okay, all right, so let's start working our way through. So my hypothesis. My null hypothesis is that the 2 means are equal to each other versus my alternative. We said, are they different, right? This is our claim. It's going to be two-tailed. This is our claim right here, okay? So I need critical values because it's a two-tailed test. There are critical values, right? Let's write it all down. So it's a two-tailed test. Right, so I need to take out alpha over 2, 0.05 all over 2 equals 0.025, right? This is a Z-test. Let's write it out because our population variances were given. 0.025. So from my table, since the population variance is known, use Z. Right, so my Z values for this associated are going to be from my table plus or minus 1.96, positive 1.96, negative 1.96. They define my critical region. Okay, so I got this from my Z table, and I could use the Z table because I was told population standard deviation. So Z alpha over 2. Right, so now our test statistic. Okay, our test statistic. Now I have to take a look at, I'm going to go Z equals X bar minus Y, oops, sorry, that's a Y bar, minus mu X minus mu Y. That's our null hypothesis, all over sigma X squared all over N, sigma Y squared all over M. Now be careful, we were given standard deviation, right? So I have to square it before I can do anything with it, okay? So let's plug these things in. So my mean for group X was 39.6. My mean for group Y was 35.4. Now my standard deviation. So now my population standard deviation for group X, 6.3. I have to square it, divided by the total number. Plus my population standard deviation for the group Y, 5.8 squared, divided by the total number for Y. We were told that there were 35 in each group, so that's where I got those 35 numbers from. So I'm going to multiply and add everything else. I get my test statistic equal to 2.90. Right, so just looking at my graph, right, my 2.9, so if my criteria is 1.96, my 2.9 is like 2.90 is like right about there. Okay, so that's going to help us think about our decision. All right, now I'm going to say my test statistic, which is 2.90, is greater than my positive critical value, which was positive 1.96, right? Therefore, we can reject our null hypothesis. Okay. Now, what I want to do is I'm going to take a side step on the same question, and I want to ask, what's our 95% confidence interval for this, for the difference in the means? Okay, so we've already kind of rolled through all the things that we know from before. Okay, so let's take a look. So I need a separate piece of paper. Using the same question, I rolled through that same thing with the 95% probability, right? But let's take a look with the 95% confidence interval. so we can see how it relates to what we've been doing so far. Okay. So now our question, so this is example 1. Our question is, what is the 95% confidence interval for the difference in means? So let's go ahead and try that. So that means I'm going to go x bar minus y bar, our difference in means, plus or minus z alpha over 2, sigma x squared L over n, sigma y squared L over m. Right? You can see how these are related, right? You can see where we're getting our values from. Okay, so that means I'm going to plug in my values. So 39.6 minus 35.4 plus or minus 1.96 radical 6.3 squared over 35 plus 5.8 squared over 35. Okay, parentheses around here so you can see. All right, so that gives me a 95% confidence interval that says I'm going to go. Let's see, what did I? Okay, right. I wrote it out differently down here. Okay, so this is if I write this out as 4.2 minus 2.8 less than mu of x minus mu of y, which is less than 4.2 plus 2.8. So this is like saying 4.2 plus or minus 2.8. And I write it out. My difference in population means 4.2 minus 2.8, 4.2 plus 2.8. That means that I've got 1.36 y, which is less than 7.037. Okay, so my 95% confidence interval for my difference in the means, this is 95% confidence interval for difference in means. Now remember, we rejected the null hypothesis. We said that the difference in the means was not equal to 0, right? I mean, so the whole idea was that there's no difference in the means. That was our null hypothesis. We rejected that and said there actually is a difference in the means. So let's take a look. Our confidence interval, right, does not contain 0. Okay, so let's go back and think about this. So if the null hypothesis is true, which means that the difference in the means is equal to 0, right? There's no difference between these two, right? I'm going to say mu x equals mu y, which is like saying mu x minus mu y equals 0, right? So if there is truly no difference in the means, okay, 0 will be within my confidence interval, okay? If hx is true, h not is true, then 0, which is, that means that there's no difference in the means, will be in the confidence interval. Okay, if we're going to reject the null hypothesis and say that the difference in the means is not 0, reject our null hypothesis, which means that the difference in the means is not 0, okay? So that means like mu of x is not equal to mu of y, right? So if I subtract them out, right, they're actually significantly different from each other, then what we see in our confidence interval is that 0 is not there. 0 will not be in the confidence interval. Okay, so let's go back, right? Our original statistics on our example, we went through the hypothesis, critical values test. We made the decision because our test statistic was within the critical region, right? It was greater than our critical value, okay? So we rejected the null hypothesis and we said there is a difference between these two means, right? Now, when we do our confidence interval of these two means, I subtract the two means plus or minus their basically pooled variance, right? 4.2 plus or minus 2.8. I come up with a confidence interval of the difference of those two means as 1.36 to 7.037. There's no 0 within here. If there's no 0 in here, that means that there's no that there isn't that there is a difference between the two means. Because if I subtracted them, and if I got 0 somewhere within that confidence interval, that means that I could say with confidence, or 95% confidence, that there's no difference in these means. But if there's no 0 in there, I can say that difference between the two means is not included in my confidence interval. Okay. So it's a really interesting point about using confidence intervals to help you make a decision criteria. Okay, so we ran through the very first part with our typical way of doing it. Okay, hypothesis, critical value, test, statistic, decision. Okay, we can do this again. We can say our hypothesis, our confidence interval, right? Our decision is going to be, is 0 within that confidence interval or not? Okay. All right. So let's keep that in mind. I'll include that also when we do our solution set. So that's when our population variance is known. Now remember, when our population variance is not known, we're going to use a t-test for when the population variance is unknown. Okay, so let's just write that up. This is for our difference, bar minus y bar, plus or minus t alpha over 2. Okay, we're going to use our sample variances. Okay, now what this means, and I'll put a box around this, gives us my confidence interval based on some alpha that we've specified. Okay, so what this means is I've got x bar minus y bar minus t alpha over 2. Okay, and that's like saying my difference in the means, I'm 95 or 99%, whatever, confident that the difference in the means is going to be between this value and this value, plus t alpha over 2 samples. Okay. And again, we're going to be looking to see in our confidence interval if there's a 0 there, right? Because if there's a 0 within our confidence interval, that means that I am, whatever, 95% confident that the difference in the means is equal to 0. If it's not there, then I can say, I can reject our null hypothesis and that they're actually different. Okay, so example 2 uses this t-test. All right, you guys will have this page right here before I do the lecture examples. Example 2 says, a study was done to examine the number of sick days that men versus women take. A random sample of 9 men, let's start underlining things, 9 men found that a mean number of sick days was 5.5. Okay, so maybe that's going to be my random variable x, with a standard deviation of the sample equal to 1.23. So we're knowing, okay, I don't have the population standard deviation, so I'm kind of already starting to think I need to do a t-test. Random sample of 7 women found that the mean number of sick days is 4.3, with a standard deviation of sample days is this. Find the 95% confidence interval for the difference in these two and use it to make a decision about the claim that the difference in the mean sick days taken. Okay, so now what we're doing is we're going to use our confidence interval to actually do our hypothesis testing. Okay, so let's start writing down stuff that we have. So I'm going to write down my formulas, x bar minus y bar plus or minus t alpha over 2. I'm doing a t-test, right? And I'm going to assume that the data is normally distributed. I'll write it down. Assume data is normal. It should have been written down there too. So t alpha over 2 s x squared all over n plus s y squared all over m. Okay, so that's the basis for my confidence interval. My degrees of freedom, because remember t is based on degrees of freedom, n plus m minus 2. Okay, so let's start thinking about what we have. So my x bar, we were told, is 5.5. Okay, my sx squared is going to be, they gave me standard deviation, so that's going to be 1.23 squared, which is, we'll come up with that later. Y bar is equal to 4.3. Y squared is equal to, they told me 4.3, 19 squared. Okay, my n is equal to 9, my m is equal to 7. Okay, my degrees of freedom, I add these two up and subtract out 2. My degrees of freedom is equal to 14. I need the degree of freedom to look up on my t-table. Okay, so alpha equals 0.05. There we go. We were given that, right there. Find the 95% confidence interval, which means my alpha is 1 minus 0.95. So t alpha over 2 and I've got n plus m minus 2 degrees of freedom. So what I'm looking at is t 0.025, 14. I use my t table, look for 14 degrees of freedom for the 0.025 probability, and I get 2.1448. And this comes from my table. Okay. So let's come up with our 95% confidence interval. Okay, so I'm going to start plugging things in, right, from based on the formula that we had at the beginning. So I'm going to say the difference in the means 5.5 minus 4.3 plus or minus 2.1448. That comes from my t table, right? 2.23 squared all over 9 plus 1.19 squared all over 7 square rooted. Okay, right? Standard deviation squared to give me my variance divided by the number that we have. Okay, so that's going to give me 1.2 plus or minus 1.305 as my confidence interval. I'm going to write it out a little bit differently so you can see minus 0.105 is less than the difference of my means, which is less than 2.505. All right, so I'm looking at this, right? My difference in my means, my null hypothesis is that there's no difference, right? So I'm looking to see is there is 0 within my confidence interval. I go from minus to plus. Okay, there's a 0 in there somewhere. Okay, so now based on my confidence interval, I'm going to make a decision. Okay, so since 0 is contained within the confidence interval, right, that means I can assume that there is no difference in the means. We can say there is not enough evidence to reject, sorry, let me write this out better. Reject what would have been our null hypothesis, that the means are equal to each other. So we are failing to reject, right? So we say, therefore, fail to reject null hypothesis that the, we don't ever say that we're going to accept that the means are the same. We're just going to say we're not going to reject that the means are different. That we're not going to reject that the means are the same. Okay. All right, so we're using our confidence interval to help us make a decision. But you can see, remember from question 1, it's a similar process to what we did when we actually went through our hypothesis, test, statistic, critical value, and comparison. Does anybody need some time to keep writing this before I move on? Okay. So we did a z-test for when the population variances are known, a t-test for when the population variance is unknown. Now let's talk about proportions. Okay, so we're going to do comparing two proportions in our confidence interval. Okay, so now remember our proportion, our estimators, Ex hat minus Py hat, our difference, plus or minus Z alpha over 2. Now, instead of doing a pooled, it's the values that you would get with our pooled proportion estimator are very similar to the values you'd get for the individuals. But now, since we're doing a confidence interval based on these two proportions, I'm going to use my individual Px hat and Py hat. So Px hat 1 minus Px hat all over n plus Py hat 1 minus Py hat all over m. I'll put a box around that and a star. Okay. So this is going to give me, right, let's write this out in terms of our, I'll write it in different colors. Let's write this out in terms of our estimate for the population proportions, right? So what I would say is this would be hat minus Py hat minus Z alpha over 2 x 1 minus Px over n y, that's y, minus Py over m. Okay, and that's Ex minus Py. This is our null hypothesis about our population proportions. And that this difference here is less than Ex minus Py, this is a y, plus Z alpha over 2. Same thing. Rooted. Okay, so we're coming up with some confidence interval around our estimate of the population proportion. Okay, so we're going to use this in our third example. Okay, you guys all good with writing that down? Okay. All right. So example 3 says, do the 95% confidence interval on the difference in proportions for vaccinations in small versus large nursing homes. This is what we did in the previous section, right? Example 1, chapter 9.4. So 12 out of 4 randomly selected small nursing homes, and 17 out of 24 gave it for large nursing homes. So just kind of remember what the data was. All right, so let's remember. Ex hat, excuse me, was 12 out of 34, which gave us 0.35. And then I'm just going to write 1 minus Px hat is equal to 0.65. Just so I'm kind of prefetching these values here. Py hat is the other one, 17 out of 24, which we said was 0.71. 1 minus Px hat is equal to 0.29. Did I make a mistake on this math? Yes, no, it was fine. Okay, good. All right, 7.1. And then our alpha, we said 95% confidence interval, so our alpha is 0.05. Okay. Now, when we're going to go to do this, our z alpha over 2 plus or minus 1.96 from our table. Okay, we get that from our table. Okay. Now, I'm going to say the difference in our proportions. So I'm going to use x hat minus Py hat plus or minus z alpha over 2. I'm going to use the individual values. Come up with our confidence interval. I'm going to fill in the blanks on that. Okay, so this is going to be 0.35 minus 0.71 plus or minus 1.96 times all of this stuff here. 0.35, 0.65 all over 34 plus 0.71, 0.29 all over 24. Okay, multiply it out. I'm going to get minus 0.36 plus or minus 0.242. Don't worry that your confidence interval is going to be negative. You got negative values in there. All we're doing is we're seeing that the difference in the means, right? Difference in our population means is between this minus this and this plus that. Let's write it out. So we're going to write our 95% confidence interval of the difference in the proportions is equal to minus 0.602. So I subtracted minus 0.36 minus 0.242 and minus 0.118. Okay, so this is like saying minus 0.602 is less than Px minus Py, which is less than minus 0.118. So I'm looking at this. You see a 0 between these two. No, I don't see a 0. So my difference in the means is down here. It doesn't incorporate 0, right? So what I'm going to conclude is the interval does not include 0. If it did include 0, that would mean, you can't say that, which would mean that the difference in the proportions equal to 0. There's no difference in the proportions, right? So it doesn't include 0. So therefore, what I can do is I can reject our null hypothesis, which says that there's no difference within them. Reject our null hypothesis, which we did in chapter 9.4 in our two-tailed test. You should get the same result, because I mean the 95% confidence interval is the same thing as a two-tailed statistical test using the same alpha value. It's just another way of representing it. Sometimes people in the public like confidence intervals. They like to kind of see the data represented that way, and then you know how to draw your conclusions based on that. Okay. Okay. You guys good so far? All right, so last example, bear with me, and then we're all done with chapter 9.5, and then basically all done in general. Let's just go through our last example. So example 4 says, what's the prevalence of anemia in women? Anemia is an iron deficiency in developing countries given the following data. We've got African women and women from the Americas, so Central and South America. Okay, so we need to think about, right? Let's fill it out. So our sample proportion, our sample size divided by with a number here. So I'm going to go 840 divided by 2100 is going to equal to 0.4. 323 divided by 1900 gives me 0.17. 1900. Okay, so I'm filling in the blanks on that. Okay, so what we want to do is find the 95% confidence interval for our difference in these two proportions here. Okay, so let's kind of write down like the stuff that we have here and what does it all mean. Get this organized. Okay, so N1 is the number of African women sampled, which is 2100. Okay, our M is the number of women from the Americas sampled, and that was 1900. Okay, so I've got my X, right, is my number of the African women with anemia. Right, which is equal to 840. I'm just summarizing what our data is here so we can see it. Y equals the number of women from the Americas, anemia, which was 323. Okay, so let's come up with our proportion values. Okay, so my px is going to equal to my px hat, right, is my x over n, right, which we did before. So 840 all of 2100, which is equal to 0.40. My py hat is our y over m, which is 323 all over 1900, which is 0.17. Okay, so now we want to be able to look at our total populations. So px, this is my total population proportion. This is the proportion of all African women with anemia. And then py is the proportion of all women from the Americas with anemia. Okay, so that's our background. Let's come up with our z's. So z alpha over 2, we're told 95% confidence interval. So alpha over 2 is 0.025. That gives us 1.96. Okay, that goes into my formula. Okay, so my px hat minus py hat, okay, sorry, plus or minus z alpha over 2. And now, because I'm doing a confidence interval, I'm going to use my individual proportions instead of a pooled proportion. It's a little bit more exact. Your values for the pooled come up very similar. It's a little bit better to use your exact numbers if you can. So px hat 1 minus px hat all over n, py hat 1 minus py hat all over m. Okay. Let's come up with our difference here, our confidence interval. So let's put things in. 0.4 minus 0.17 plus or minus 1.96, right, from our z value, times 0.4, 0.6 all over 2100 plus 0.17, 0.83 all over 1900 square rooted. Don't forget the square root. Okay, so that's going to give us 0.23 plus or minus 0.027, okay, which gives us 0.203 all the way. So I subtract 0.023 to minus 0.027. That's going to give me this 0.23 plus 0.027, 0.257. Okay, this is our 95% confidence interval of the difference in proportions, okay, between African women and women from the Americas. It doesn't contain 0, which means we can conclude that they're different. What does that mean? I'm going to put this out in words, okay? So we can conclude proportions are different since our confidence interval does not contain 0. Okay, but what does this mean? Let me write it out also in words. So we can say we can be 95% confident that there are between, watch what I'm going to do. I'm going to take these values here, 20.3% and 25.7% more African women with anemia than women from the Americas. Okay, that's just putting it in words just so that you know how to interpret this confidence interval here in terms of the difference in the means. Okay, it doesn't include 0, so we can't say, well, let's conclude that these two proportions are equal. They're equal representations of women with anemia in both the Africas and in the Americas, right? So we can conclude here these are positive values. We were subtracting Africa minus the Americas. We got a positive number. That means that we have more people with anemia in Africa than we do in the Americas, more women, okay? All right, okay, confidence intervals, 2 different means. You know the population standard deviation, you don't know it, and proportions, okay? Also, when we look at our confidence interval, if it contains 0, that means that we can not reject our null hypothesis, because our null hypothesis says, right, that there's no difference in these means. So if it contains 0, our confidence interval, that means we can conclude that there's no difference between these two means. If our confidence interval does not contain 0, okay, that means we can conclude that these two proportions or population means or whatever are different from each other, okay? So that wraps up all of our material for the course. Okay, so that's chapter 9.5. I will scan in the lecture examples later today and then upload them so you guys can have them. For the next couple classes and for office hours too, you guys can come and ask questions. Like I said before, you know, focus on things that from the homework, and our next exam, which is more like a midterm exam, we'll cover material that's just based on statistics. Okay, so a lot of hypothesis testing. You can expect hypothesis testing where we know the population standard deviation, we don't know the population standard deviation, we have proportions, we're going to do confidence intervals of just single samples in the population, we're going to do confidence intervals and also statistics on differences of two means, okay? Also, you want to be able to take a look at things like checking the variances, right? Are the variances equal or not? So if they are equal, then I can use I would do an F test for that, right? And if they are equal, I could use a pooled variance. If they're not equal, I'm going to use counting the individual variances in my test statistic. Okay? Are you guys? So that's it. And I hope you have a great day. And